Hello everybody, we move to lecture 2 of this particular course. In lecture 1, that is in the previous lecture, we had seen why digital technology is important, what constitutes digital technology, the importance of switching, association of switching with logic relation, and use of diode as a switch. So, this is what we had seen earlier, and in that discussion we had seen that diode as a switch can be used for developing and OR logic. Okay? We left ourselves with a question that whether we can get inverter logic or NOT logic using diode, which we found that from our common understanding it is not possible, but transistors can be used for generating NOT logic or inverter. Okay? So, in today's lecture we shall cover transistor as a switch. So, we shall look at its input output characteristics and some important parameters like noise margin, transition width, logic swing and fan out. So, we start with a basic circuit of a very simple circuit of a transistor based inverter. So, what we see in the left hand side of this slide is a circuit where we see this is a NPN transistor, bipolar junction transistor, this is the base, this is the collector and this is the emitter. Okay. So, this collector is connected through this RC to power supply VCC, a positive power supply, we consider 5 volt here, and the base is connected to a input voltage, the V in, through a resistance which is RB, base resistance RB. This is collector resistance RC, okay, and output is taken from collector C, right. So, this is the basic configuration which we shall examine. Now, if you look at this circuit and we try to plot V in versus V out, V in versus V out, okay. So, this side, this x axis is V in, okay, independent variable, and the y axis is the dependent variable V out. So, how this circuit will work? Right in the beginning when V in is 0, okay. So, the transistor is in off state. So, at that time what will be the output? Since this transistor is off, no current is no IC current is flowing, no collector current is flowing. So, collector current, that IC into RC, this drop VCC minus IC RC, that is your V out, this is your V out. Okay. So, since IC is equal to 0, so the voltage that you get here is the VCC, okay, which is about 5 volt over here, right. So, how long it continues? It continues up to a maximum voltage, when this base emitter junction becomes sufficiently forward biased, so that this starts conducting, okay, this transistor starts conducting. So, that maximum voltage we define here in general as VIL. That means the voltage at the input side which is considered low, the maximum of the input voltage at the input side which is considered as low. Any voltage less than that, what will be it be, how will it be considered? It will be considered as low, logic low only, because at that time you see the output is remaining at high voltage, which is an inverter action. I mean, at the first part of the inverter action, we shall see the other part also, when input is high, whether the output is low or not. Okay. So, input is considered low up to a maximum point VIL. Is it clear? So, after that the transistor starts conducting. So, this from cutoff region, transistor enters into next region. What is that? Active region, right. And when the transistor starts conducting, IC is getting increased. What will happen? This voltage, this V out will slowly come down. We shall see later for a this particular arrangement under certain approximation, this fall is approximately linear. That relationship we shall soon see. Okay. So, this is now the current is increasing, voltage is getting increased, so IB is increasing, accordingly IC is increasing, beta IB is the current IC value in the active region, and this will continue till it enters the next stage, what is known as saturation, right? What is known as saturation, when both base collector and base emitter junctions are forward biased. Okay. So, at this point, what is the voltage here? It's approximately some 0.2, 0.1 volt or whatever, I mean depending on the transistor that you are using. Okay. So, that is the maximum voltage at the that is the minimum voltage at the input side, which is to be present, after which the transistor will move into saturation. Okay. Any voltage higher than that at the input side, it will move into saturation. Is it clear? Let me repeat once more. So, from VIL, when the transistor starts conducting, which is in active region, okay, gradually with increase in Vin, base current increases, corresponding collector current increases, Vout starts falling, it continues up to a level which is known as when it enters the saturation. So, after that any increase in the voltage, Vin, the transistor remains in saturation. Before that it comes out of the saturation. Is it clear? So, we tell that particular voltage as VIH. Okay. So, what happens at that voltage? At that voltage we know firmly that the output is in saturation and the voltage here is about 0.2, 0.1 volt or so, which is considered as low at the output level. So, any voltage higher than that will be considered as, at the input side, will necessarily make the output low. Okay. So, the other way speaking, what is the significance of VIH? VIH is the minimum voltage required at the input side, okay, which is treated as logic high. Any voltage higher than that at the input side will be treated as logic high. Okay. Is it clear? So, we see the relationship, the inversion relationship. Input is low over here, okay, output is high, input is high, output is low, right. And we see there are two other voltages. This is the VOL, that is the voltage at the output side which is treated as low. Any voltage less than that will be treated as low, and VOH is the voltage at the output side which is treated as high. Any voltage higher than that also will be treated as high. This is in general we see a characteristics of a inverter, which is also kind of getting there is a correspondence between this transistor input output characteristics. Is it clear? So, we would like to do some sort of quantitative analysis, and we shall keep it very simple for our understanding of the way the logic circuit or digital circuit works, and we shall keep say RB 10 kilo ohm. Okay. So, 10 all zeros are there, so it will help. RC 1 kilo ohm, beta, transistor beta, the current gain as 50, beta F stands for beta forward, beta R is beta reverse beta, that we shall take up later. This VB on, when the transistor is on, we shall consider the voltage at which it becomes on remains on is 0.7 volt, and when it goes to saturation there is a small increase in this voltage, but again as I said this is an approximate analysis, we shall keep it at 0.7 volt only. Okay. But actually there will be small increase in this voltage when it goes to saturation, and VC saturation we will consider as 0.2 volt, which again as it increases falls little bit. Okay. So, this is what we are going to do. Right. So, with this let us look at that characteristics. Okay. So, the first thing that we shall try to get is at which voltage this fall starts occurring, right. And as we know in this particular case it is very simple, this VIL in this case is nothing but the voltage when it comes out of cutoff region and enters the active region, and it occurs based on whatever values we have already taken, occurs at 0.7 volt, right. So, the coordinate of this is 0.7 volt and 5 volt, 0.7 volt and 5 volt. Okay. This is this coordinate that we see for the analysis that we are making, and this is also known as edge of cutoff, edge of cutoff. That means, at this point it is just coming out of cutoff. Is it clear? Next we shall see what happens when it enters into active region. Okay. So, when it enters into active region, current flows along this loop, two loops that we can see over here. One is along this loop, another is along this loop, right. So, we shall apply Kirchhoff's voltage law along this loop, and from that we shall do a quantitative analysis, right. So, when we apply along this particular loop, what we see? This voltage IB will be V in minus VB on the voltage drop over here divided by RB, right. From that we can see that voltage current through this IB is V in minus VB on, that is the rest of the drop is over RB, okay, divided by RB is what is your IB. Is it clear? Now, in active region we know IC is equal to beta f IB, okay, and in active region this is the other loop along which we are applying KVL. So, this is 5 volt, that is the VCC that we have already mentioned. So, this is generally speaking we write it as VCC because we can change it some other voltage other than 5 volt if so required. For generalization purpose we write this as VCC. Okay. So, V out is nothing but VCC minus ICRC, and this IC is nothing but your beta f IB, we replace it with this one. Now, this IB, this was your equation 1 and this is your equation 2. So, if you take the IB from equation 1 and combine and place it here, so this is the thing that this is the relationship that you get. Is it okay? So, V out is equal to VCC minus beta f IB RC. So, RC is there, IB is nothing but your V in minus VB on divided by RB. Is it fine? So, as long as it is remaining in active region, this is the relationship it will follow, okay. And we look at V out versus V in, rest of all are constant. As I said, VB on will slightly change with increase in V in on, so we are neglecting that part, it is an approximate calculation, right. So, rest of them all the parameters are constant. So, we have V out and V in, relationship between them is linear, straight line, okay. Straight line with a negative slope of what? Minus beta f RC by RB. Is it fine? So, if we want a faster fall, right, we want more often the circuit remains in one of the two stable switch state, that is logic 0 or logic high, then we would like to have this transition region, this active region which is also known as transition region, that width as small as possible, okay. So, we would like to have a faster fall. So, in that case we would like to have RC more compared to RB, we would like to have increase in RC, but again we shall see later, if we increase RC, then the circuit's current delivery capacity, the IC part of it gets reduced, which actually makes it difficult for the circuit to get connected to many other circuits. That particular thing also we shall see today, okay. So, there is always, when you talk about design, there is always a trade off, okay. But this is what we take from this particular discussion, is that there is a linear relationship and the slope is negative for the circuit in the active region. Okay. Now, next is saturation region, right. So, in this saturation region again we would be interested to see when it enters saturation. Okay. As long as it is remaining in active region, it is falling linearly with a negative slope. That part we have already seen. Okay. That is what we have already noted in the previous slide. Okay. So, this particular point, these we define as edge of saturation. When it just enters the edge of saturation, which consider that it is still following this previous equation. After that it goes into saturation region, it is no longer that linear relationship that we will be maintaining. So, edge of saturation it is still maintaining, right. So, at that time this V out, when it just enters edge of it is at the edge of saturation, is VC saturation, right. So, at that time the current, the IC we define with a suffix edge of saturation when it is just entering here is VCC minus V out is now VC sat divided by RC. So, that is 5 volt we have considered as VCC minus 0.2 volt divided by RC. RC is equal to 1 kilo ohm, that is 4.8 milliampere. Okay. If we increase the RC, this current will reduce, which will have a bearing with later in some other cases. So, we cannot just change it the way we like. We have to look at other considerations in a situation like this. So, this is edge of saturation IC, right. So, edge of saturation IB is what? This IC edge of saturation divided by beta, because it is still in active region, it is just entering the saturation region. So, 4.8 divided by the beta forward, which is 0.096 milliampere, simple calculation, right. So, at that time what is the V in, right? We refer back to that equation 1 that we had before. So, V in is equal to VB on, right, the base emitter drop and IBRB drop. So, IB edge of saturation into RB in the KVL in that base emitter junction, that particular loop, right. So, in this loop, this is the loop, in this loop, sorry. So, this is the loop that I am talking about. Okay. So, we in this particular loop, when we impose these values, right, we get 0.7 volt, IB edge of saturation 0.096 volt and RB we have taken as 10 kilo ohm. So, 1.66 volt. Okay. So, thereby we get this particular point also edge of saturation, which is also important to us, and this coordinate is 1.66 volt and 0.2 volt. Is it fine? Okay. So, any voltage greater than 1.66 volt at V in, definitely the circuit is in the saturation, right. So, that is the significance of VIH. I was trying to tell that this is the minimum voltage required at the input side, okay, which can be treated as logic high, which will ensure for the inverter that the output remains at logic low. Clear? Right? Now, we come to some important parameters: noise margin, transition width and logic swing. Okay. Transition width we have already seen, but again more formally we shall introduce ourselves to these terms over here. Okay. So, in the left hand side what you see is a generalized representation, not specific to the example that we have taken. So, we have taken the example to make a better understanding of these different terms and all using a simple transistor inverter. Actual circuit will be more complex, which we shall take up later, right. So, this is the output side. Okay. So, VOL we have already seen, the voltage at the output which is treated as low, any voltage less than that will be treated as low. In that example 0.2 volt, any voltage less than that treated as logic low. This is the shaded region over here. Okay. VOH, voltage at the output side, okay, minimum voltage which is treated as logic high. Any voltage above that you will be treated as logic high. So, it was 5 volt there, and any voltage more than that 5 volt will be treated as logic high without any ambiguity. Clear? And then the logic swing, this is defined as logic swing, is the difference between VOH and VOL. Okay. Now, if we look at the input side, what is happening? This VIL, as we have already seen in that particular example, but it is true for every other cases for an inverter like this, that from 0 to VIL, this is treated as logic low. Any voltage even less than 0 also, because of noise and other things, if it is less than VIL, as long as it is less than VIL, it is treated as logic low, the input is treated as logic low, right. And at the input side, any voltage greater than VIH will be treated as logic high. Okay. In that example, it was 1.66 volt. Any voltage more than that, it will be treated as logic high. The output will be low at that time, right. So, the difference between VIL and VIH, the time, the phase or the duration, if we are continuously increasing the Vin's input voltage, that is your transition width, the active region in where it is staying. Okay. So, after understanding these terms once more, now we define noise margin high, noise margin low as VIL minus VOL. What is the significance of it? The significance of this is this, that up to VIL we are treating this as logic low. Here, if this inverter is connected to another inverter, another similar device to the next stage, so when it is at logic low, what is the voltage it is offering? 0.2 volt or less, maximum voltage is 0.2 volt. Okay. Now, imagine some noise gets corrupted, additive noise, right. So, if it is a 1 volt, 0.1 volt noise, so the voltage at the output will be 0.2 volt. Okay. So, what I mean over here, let me draw a diagram which might make it clear to you. So, I am talking about this is being connected to another device, another such inverter or other gates, right. So, here it is 0.2 volt maximum, when it is treated as logic low, it can be less than that, but let us consider the limiting case. Okay. And then noise gets added, say additive noise is getting added over here. So, this is noise. Okay, noise, right. So, how much noise you can allow, so that this low is treated as low here. The maximum voltage that it can treat as low is 0.7 volt. Okay. This is maximum at the output when it is logic low is 0.2 volt, it can be less than that. So, what is the difference? The difference is the maximum voltage that can be accepted as noise, which is added as with positive polarity. If it is negative value, say 0.2 volt and noise is minus 0.1 volt, then there is no issue. Okay. But noise with positive polarity, if it comes, then this is the thing that we need to remember. Is it clear? So, that a 0.5 volt margin is there with me. So, this is noise margin low. Generally speaking, for any such situation where VIL and VOL, the way it is defined, this is the difference is the noise margin. In this specific example that we have taken, from which you are trying to understand these terms, it is 0.7 minus 0.2 volt, which is 0.5 volt. Okay. So, similar thing, noise margin high. So, when the output is at logic high, say VOH, right, and at the input it has to be treated as logic high, right. So, what is the, now if noise gets added, but if it is positive polarity, it will be VOH plus some value, then there is no issue, this we are in this region. But if it is negative polarity, now the polarity of noise, if so negative, then we are in a bit of concern. So, this VOH can come down. If it comes down and crosses VIH, then we are in a problem. The input will not be treated as high. Okay. So, this VOH minus VIH is the noise, the margin of noise that it can accommodate. So, accordingly, these two terms are defined, and in this specific example that we have taken, it is 5 volt minus 1.66 volt, which is 3.34 volt. So, transition width of course is the difference between this VIH and VIL and logic swing. So, these definitions that you see, these are general irrespective of the example we have taken, okay, and it is applied to any logic family and the corresponding gates. Okay. Now, we shall end with one important term called Fanout, and the example that we are talking about noise margin, if we take it a little bit further. Here what we see is that a transistor, a gate will never work in isolation. We know that hundreds, thousands, such gates are working together in an integrated circuit. So, this particular inverter is connected to many such inverters, okay. And when the input, so this is the driver and these are the loads, okay. Load 1, load 2, load n, we shall figure out how many loads can be connected, okay. So, at the input side, when the input is say logic high, what will be the value here? Output will be low, say 0.2 volt or so, or even less, okay. Then none of this load transistor will be on because the presence is 0.2 volt, okay. So, you can connect, since it is not drawing any current, you can connect many such load transistor, load gate without any difficulty, load inverter without any difficulty. Is it clear? But there may be an issue when the input to the driver is low. So, this is the input to the driver, when it is low, the output is high, we have already seen, right, the characteristics part of it, isn't it. So, the characteristics was like this. So, when input is low, the output is high, so this particular thing, right. So, this output high, we are connecting to many such gates, right, and whenever it is connecting, these are drawing base current, right, and though there is no current in this direction, but there is a current in this direction, for which there will be ICRC drop, more such connection, more amount of current has to be delivered, and the voltage will keep coming down, it will no longer remain 5 volt. So, how much it can come down, so that it is still treated as logic high at the output side, there is a limit on that, right, that is 1.66 volt in this particular example, after which it will not be treated as logic high, it will enter into the active region, these load gates will be entering into the active region, okay. So, that will decide how many such gates can be connected, okay. So, this is the way we calculate this one. So, for the VIH, we said this limiting case is the 1.66 volt, and driver at that time how much current it can deliver, VCC minus Vout, that is 1.66 volt divided by 1 kilo ohm. So, that is the 3.34 milliampere, that is the maximum current it can deliver without this voltage going below your 1.66 volt, the limiting value, after which it will no longer be treated as logic high at the load gate side. Okay? And for the load gate, when it is high, what is the current it is drawing? We have already calculated this one. Okay? So, Vout minus VBE sat divided by VBE saturation divided by RB. Okay? So, this is your own 1.66 volt. Okay? 1.66 volt limiting condition we are talking about, and this is 0.7 volt over here, right, divided by RB. So, this is 0.096 milliampere. This is the current that is one load gate is taking. Okay. So, how many such load gates are there? How load gate you can connect by this? Just divide the amount of current it can deliver divided by this one, and this number is quite big. I mean 34. We have to consider more, other issues into it, and then it will be clearer. Okay. So, this is the last slide for this particular discussion. So, what is the effect of noise margin? Okay. So, earlier when we talked about when it is, we are bringing it down to 1.66 volt. Okay. So, what becomes the noise margin? There is no noise margin there. Okay. So, if you want to, because whatever was possible, you have brought down to that particular level, any noise now getting added at the output 1.66 volt, and some noise with negative polarity minus 0.1 volt or so, okay, it will not be treated as logic high anymore. So, there is zero noise margin. Okay. So, if you want to keep a noise margin of a desired value depending on the environment in which it is operating, then you have to consider that also into your calculation, that factor. So, this 1.66 volt will no longer be 1.66 volt, it has to be plus the noise margin that we are talking about, so 0.5 volt, that makes it 2.16 volt. Okay. So, then the driver side current, the maximum current it can deliver is VCC minus Vout. Now, it has now considered VIH as well as the noise margin. Okay. So, that makes it 2.84 milliampere, right, and at that time what will be the load current for each of the gates? So, IB load is 2.16 minus 0.17 divided by base resistance 0.15 milliampere, and then you look at, if you just reduce the if you just do the division, the number comes down to 19. From 34 it has come down to 19, drastic fall, isn't it? So, if you have more noise margin, then there will be more such issue, right. So, I mean more fall in the number, and then there are other parameters also that we have not considered in this discussion, like the beta that you have considered 50, it might, when you use the transistor, it could be 40 also, it could be 30 also, depending on the make, and there will be a transistor to transistor variation. So, you have to keep a consideration like worst case scenario also. So, each of these parameter might vary and may not be the V saturation also we have said it is not exactly 0.7 volt, can vary little bit. VCC can vary, 5 volt power supply maybe 4.5 volt to 5.5 volt. So, these are the different things for which the actual value will see that for this particular configuration from 34 to 19, now practically it can come down to 5, approximately 5 or so. Okay. So, these are some important parameters. With an example we have noted. So, these are the references. So, quick summary, the transistor can be used for a NOT logic. The cutoff and saturations are two stable states. We have seen the input and output characteristics, and from that we have derived some very important terms, generalized terms, noise margin, transition width, logic swing, and we have taken up one example cases and put some values and understood its significance. And fan out is also another important parameter that also we have seen what is it, what does it mean and what is its significance, how to calculate it. Thank you.